In writing electron configurations, you need to use your periodic table and make sure you understand the blocks. This particular periodic table is labeled according to the S, D, P, and F block. The difference on this one is that it doesn't have helium where your helium is on the periodic table. And so they're actually, helium should be over here right above group 18, or right in group 18. But it is an S2, so that's why this particular periodic table has it written in group 2. So in this problem, it's going to ask, we're just going to go through a series of questions about selenium, so Se. So we're going to look at Se and try to get there and write its electron configuration. So the first thing it wants us to do is to write the complete electron configuration for selenium. So that's question number 1. So I'm going to do it right under the periodic table so you can see where that's at. So selenium has 34 electrons. So we're going to just go through and stop at what I call the bus stops, which are full shells or full orbitals, and those are going to be at the end of colors. And so our first bus stop, you can see, is helium. So helium is 1s2, and your helium is over on group 18, but it's still 1s2. The next stop is always beryllium, so that's going to be 2s2. And we're going to continue through our stops, and so neon is our next stop, which is 2p6. Next stop is magnesium, which is 3s2. Continuing on to argon, which is 3p6. Then to calcium, which is 4s2. Then notice that the D's, I have it written on here, but it's n-1. What that means is that the n number, the energy level number, is going to be down 1. So it's on the 4th energy level, but 4 minus 1 is 3. So for zinc, I write down 3d10. And then I don't have to go all the way to the krypton bus stop because I'm stopping at selenium. So selenium, which we can see, is 4 and then p4. So then another little check we can see really quickly is what the little exponents add up to. So 2 plus 2 plus 6 is 10, plus another 2, 6 and 2 is another 10, so that's 20, plus 10 is 30, and then 4. So we see that this is equal to 34. And again, remember that these numbers right there, all along, these are the exponent numbers, are the number of electrons. And so those all have to add up to the number of electrons that are in selenium. So that's number 1. So the next thing I'd ask you is to write the noble gas notation. So to do noble gas notation, you go over and you look, here's selenium. Selenium is number 34. And so when I take a look at number 34, I look at the closest noble gas to number 34 without going over 34. So the noble gases are this last column. So when we look, this column here, this is the noble gases. So I can only use one of those. And so I look, closest to 34 without going over would be argon. So what we do for the noble gas notation is we put argon in brackets. So we're basically saying is include all the electrons up to argon, which is 18 electrons, and then now start your bus stops. And so after argon, my next bus stop would be calcium. So that's going to be 4s2. And then, again, 3d10, 4 zinc, and finally we get to selenium, which is 4p4. Notice I did not include argon's 3p6. And that's all included in the fact that this is argon. So now we're going to do the same thing again. We're going to take a look and add up to make sure it adds up to 34. So I know that argon is 18. So it has 18 electrons. And so then I'm going to add 18 plus 2, which is 20. Plus 10, which is 30, plus 4, which is 34. So I know I'm good. It's kind of like, playing on the words, that discount double check, making sure that your numbers, your electrons, add up to the proper numbers. So then the next thing it asks you to do is the orbital filling diagram. And I just want you to do this for the orbitals that are beyond the noble gas. So we're just going to do the orbital filling diagram for the 4s, the 3d, and the 4p. So to do this, I know that every s is only one room. So I'm going to draw 1. Every d is 5, and every p is 3. I know this because it has to hold that number of electrons, and s's hold 2. There can be 2 electrons per orbital. I know that this has to hold 10 and 2 electrons per orbital, so obviously there has to be 5 d orbitals, and then p's are always 3. So I'm going to label those on the bottom, and then all I'm going to do is put the electrons on the lines as arrows. And so I know that this has 2, so I'm going to put an up arrow and a down arrow to represent those 2. The d's have 10. I'm going to put them in one at a time based on Hund's rule. And then I'm going to go back down. So that's going to give me 10. But then the last one, P4, I'm going to do 1, 2, 3, and then remember you don't pair up until you have to, 4. So that would be the orbital filling diagram. So for my AP students, this is helpful to be able to decide whether this element would be paramagnetic or diamagnetic. And the fact that it has some unshared electrons, unpaired electrons, then that would make it paramagnetic. All diamagnetic would be that it has all paired up electrons. So if it was just zinc, then that would be diamagnetic. And so what happens is paramagnetic means that it would have some magnetic properties. So now the next thing we want to look at is what is the oxidation number of Se. So if you go back over to Se, Se is in group 16. And so we saw before that if we have 16, in group 16 there are 6 electrons in the outer shell. So if we did the electron dot or Lewis structure for Se, it would look like that. And so it would love to gain 2 more electrons and then be isoelectronic with krypton. So we're going to gain 2, so we know that everything in group 16 is going to have a -2 charge. So the oxidation number for Se is a -2. And just kind of that add-on, its Lewis dot structure would have 6 electrons because it's in group 6, and it also has 6 electrons in its outer shell from, if we take a look over here, that we have 2 electrons in this S and 4 in the P, and that's the outer shell, so it's a total of 6. But it's so much easier just to look at the group number. Group 16, cover up the 1, so in 16, so it has 6 electrons in its outer shell, so 6 dots. So for number 5, we want to look at the which ones are isoelectronic. Isoelectronic, the word isoelectronic means same electrons. And so when I take a look at Se and I look at Se -2, I know that when it gains 2, it's going to have 36 electrons. And so what I want to see here is who else can have 36 electrons. So I know that if Br, which is 35, gains 1 electron, that it can also have 36 electrons. And so you're going to see that there's kind of a family for isoelectronics. So Se is -2, Br is -1, Kr all have 36, As is -3. 3 plus 3 is 36. 34 plus 2 is 36. 35 plus 1 is 36. We can pop over here to the ones that are positive. Positive means that you lose electrons. So 37 minus 1 would be 36. So who would be isoelectronic then with Se -2 would be, and again, I'm going to just start with krypton because they're all going to have 36. So then Br -1, As -3, Rb +1, Sr +2, Again, what makes it isoelectric means same electrons, so those guys would have the same electrons. So for my Chem 1, that's the basics that you have to do. So for AP Chem, the last thing I'm asking here are what are 4 possible quantum numbers for the last electron at the ground state for this element. So I'm asking, if we look up here, this electron in this 4p, what would be its possible quantum numbers? So what is a quantum number? Well, the quantum numbers are basically like a Social Security number for an electron, and they have 4 types of quantum numbers.
Please excuse the interruption.
So when we look at the quantum numbers, we have the n quantum number, which basically is just the energy level that the electron's going into. We have the we kind of popped over too quick. We have the L quantum number, which tells me which orbital that it's going to go in. And then also we have the magnetic quantum number, which tells me the orientation of that orbital, and then the spin quantum number. So very easily, the n quantum number, if I look back up, it's going to be going into the 4p. So it's in the 4th energy level, so the n is 4. The L quantum number has to range anywhere from 0 to n minus 1. So the max I could actually put here would be a 3 for the L quantum number. But there's very specific quantum numbers. Since this is a p orbital, I know the quantum number. So how does that work? Well, an S is going to give you an L quantum number as 0. P, its L quantum number is a 1. D is a 2. And F is a 3. So I just look up and go, okay, it's a p orbital, so I know that the quantum number is going to be a 1. So for the L quantum number, it's specifically a 1. Now for the ML quantum number, it can range anywhere from minus L to plus L. So I'm going to see that it's minus 1. So I can put either, or I see that the L is 1, so it can be minus 1, 0, or 1. So you can pick any of those. So it's always safe to put 0 for the magnetic quantum number, because there's always a 0. It's always a choice for orientation. So that's why there's 3 p orbitals, is it got those 3 orientations. And the last one's really easy. The spin quantum number, you can either put a plus or a minus 1/2, which shows the spin. So this is just some basic information about how to do electron configuration and all the things you can find out about an element on the periodic table.